Hello friends, welcome to the course Essentials of Data Science with R Software 2, where we are trying to understand the topics of sampling theory and linear regression analysis. And in this lecture, we will continue with our modules sampling theory with R Software, and we are going to handle the topic of Bootstrap methodology. So you may recall that in the earlier 3 lectures, we had considered the use of Bootstrap methodology in estimating the value of the estimator, its bias as well as the standard error. And we also considered that how the boot function works in R software. So we have now covered the theory part as well as the computation part related to the Bootstrap estimator, its bias as well as standard error. Now the next aspect is confidence interval. So you can see that up to now whatever I have done, we have used the point estimation. We have estimated the value of the statistics at a point. So that was point estimate that was obtained as an average of all the bootstrapped value of the statistic. Now we would like to estimate the confidence interval using the Bootstrap methodology. The difference between estimating the bias, standard error and confidence interval is that you have seen we have used the result like x bar minus mu upon sigma by root n follows normal distribution, normal 0 1 if sigma square is known and the population with mean mu and variance sigma square. So my data is from the normal mu sigma square, but the statistics x bar minus mu upon sigma by root n, the sampling distribution of this statistics is normal 0 1. And using the distribution of the statistics, we try to find out the cutoff values, and based on that we try to compute the confidence interval. The problem is this: the computation of sampling distribution or the determination of sampling distribution is not so easy. And without that we cannot estimate the confidence interval. So the Bootstrap methodology helps once again, and the concept of the confidence interval and the estimation procedure remains the same whatever is in the usual statistical inference. Whatever are the basic fundamentals related to the theory of confidence interval, they remain the same. The only challenge before us that how to compute the values of the parameter, standard error and distribution of the statistic. So out of these 3 components, we already have learned how to find out the value of the parameter, that is the Bootstrap estimator of the parameter. We also have computed the standard error of the Bootstrap statistics. The only challenge which is left for the computation of confidence interval, how to find out the critical values which are dependent on the sampling distribution of the statistics. So for that people have proposed different types of ways. So in this lecture we are going to consider this, and based on that we will try to construct the confidence interval. Well, let me make it clear in the beginning that it is very difficult for me to give you the entire details behind the theory and fundamentals of the construction of those 5 types of confidence interval. But still I will try my best to give you a brief overview, a brief detail. And particularly in one type of confidence interval, we also need the concept of jackknife. So jackknife we are not covering here in this course. So I will not be able to give you the more details about those things, but I will just try to show you that how the things work. And ultimately we are going to use the R software. So, our software will take care of all the theory behind the construction of the confidence interval. So, let us now begin our lecture with this note. Okay. So first I try to give you a brief overview that how do we compute the confidence interval in a usual case. Suppose if I say that I have got here a sample x1, x2, xn from some normal population with mean mu and variance sigma square, right. In this case we know that x bar minus mu upon sigma by root n, this follows a normal 0 1 distribution, and this is the sampling distribution of x bar minus mu divided by sigma by root n, right. And based on that, what we try to do, we try to write down this x bar minus mu upon sigma by root n, that will lie between minus z alpha by 2 and z alpha by 2, and the probability of such an event has to be 1 minus alpha, where alpha is lying between 0 and 1. And if you try to solve this inequality, you will get the lower and upper confidence limits, right. So, this is the basic theory what we have done. So, essentially if you try to obtain here the confidence interval, that will look like x bar plus minus say z alpha by 2 and sigma by root n. So, now if you try to identify the components of this confidence limits, so I have here the value of the statistic, that is the estimator of the population mean mu, the critical value which is obtained from the sampling distribution. This value is going to be known only when we know that the sampling distribution of this statistics is normal 0 1, and then we have the standard error of x bar, right. Here we are assuming that sigma is known. Okay. So, these are the three components. So, based on these three components, I can write a general structure of the confidence interval. So, this is what is my starting point. So, suppose if I say that theta is the parameter of interest, and this theta is being estimated by theta hat. For example, in the normal mu sigma square, I have estimated mu by x bar, sample mean. Then in this case, the 101 minus alpha % confidence interval for theta for alpha lying between 0 and 1 is given by theta hat minus z alpha by 2 square root of variance of theta hat, that is the standard deviation of theta hat or standard error of theta hat, and the upper limit of the confidence interval is theta hat plus z alpha by 2 square root of variance of theta hat, right, where this z alpha by 2 denotes the upper alpha by 2 % points on the distribution of normal theta sigma square, and we are assuming here sigma square is known. And if sigma square is unknown, then what happened, that we try to estimate the sigma square, and instead of using the standard deviation of the statistics, we try to use the standard error of theta hat, right. So, in this case we know that the distribution of the statistics in case of normal mu sigma square, if I say that x1, x2, xn are coming from normal mu sigma square, and if sigma square is not known to us, then theta hat minus theta upon standard error of theta hat follows a t distribution with n minus 1 degrees of freedom, right. So, that is what I am trying to write down here, that if sigma square is unknown to us, then the 101 minus alpha % confidence interval for theta for alpha lying between 0 and 1 is given by this interval, where the lower limit is theta hat minus the critical value t alpha by 2 at the given degrees of freedom, say df in general, into standard error of theta hat, and the upper limit is given by the same quantity with a positive sign. And here this this critical value t alpha by 2, this denotes the upper alpha by 2 % points of the t distribution with say degree of freedom denoted as df, which in this particular case is small n minus 1, right. So, this is my basic idea behind this confidence interval. And now, if you try to see, this confidence interval has got say another thing, if you try to see here, if I try to draw the sampling distribution of something, then you see here on the left and right hand side, we are trying to take the value. I am trying to divide the alpha into, say, 2 equal parts. Well, 2 equal parts are needed when we have a symmetric distribution. If the distribution of statistics is not symmetric, then it is going to be alpha by 2 and 1 minus alpha by 2. Well, I am trying to give you the basic fundamentals, so I will try to remain as simple as possible. So, we are interested in finding out the confidence interval. So, I want to find out the confidence interval such that this area under the sampling distribution of the corresponding statistics is 1 minus alpha, and the shaded area on the left hand side and the shaded area on the right hand side is alpha by 2. And corresponding to which I have to find out here the lower limit of the confidence interval and upper limit of the confidence interval. And these limits have been defined in such a way such that they are the values on the x axis here, which are trying to divide the entire area into 3 parts: part number 1, part number 2, and part number here 3. And this area has been divided in such a way such that the area in the mid, it is 1 minus alpha, and the sum of the areas on the 2 extremes, it is alpha. In this case, this is alpha by 2 plus alpha by 2. So, essentially, if you remember, what are we trying to do? This is the sampling distribution of my statistics, whatever I want to compute. So, if I try to obtain various values of statistics, and if I try to plot a density curve or a histogram, then essentially this limit, this lower limit of the confidence interval and this upper limit of the confidence interval here, these are actually the value of the percentiles. And if you remember, we had discussed this thing in case of simple random sampling also. So, here in this figure, I have denoted the 1 minus alpha percent area in the green shade and the alpha by 2 area in the red shade. So, essentially, I have to divide this entire area into, say, 100 equal parts, and then I have to find out here this value here, that what is the value of the percentile, which is trying to divide the total area into 3 parts, right, such that the middle area is 1 minus alpha and the remaining 2 areas on left hand side and right hand side in this case are alpha by 2 and alpha by 2 each. Right, and if I can find out the value of the percentile, which is indicated by theta hat alpha by 2 L and theta hat alpha by 2 U, that is lower and upper limit, then this is actually going to give us the 101 minus alpha percent confidence interval. So, this is the basic idea behind the confidence interval, that the confidence interval can be constructed or viewed what we have seen in this slide under normal or t distribution, and in principle the confidence interval can also be seen from the point of view of percentiles. Right. So, what are we going to do? We have to essentially find out the sampling distribution, and then I have to find out the cutoff values which are here. Right. So, I am trying to see here that that there are 100 alpha by 2 percent values which are below, theta alpha by 2 lower, and above theta alpha by 2 upper. And so, that means essentially the proportion of the values in the here red zone is alpha by 2 and the area of, and the proportion of the points in the green zone here is 1 minus alpha. Right. So, if I can obtain such a partition, then the estimates of this theta alpha by 2 L and theta alpha by 2 U, they can be considered as theta hat alpha by 2 L and theta hat alpha by 2 U, and which can be considered as 101 minus alpha percent confidence interval for the parameter theta. So, these are the basic fundamentals which have been used in the construction of Bootstrap confidence interval. Right. So, in Bootstrap methodology, there are 5 popular ways of finding out the confidence interval. The first methodology is without any order of preference, I am saying that in the order in which I am going to consider. The first method we are going to consider here is percentile method. So this is based on the percentile of the distribution of the bootstrap statistics. For example, I have just explained it. Second thing is this: we assume that the distribution of the statistics is normal 0, 1, and then we try to find out the percentile of the standard normal 0, 1 distribution, and we try to construct the confidence interval. And similarly, as I explained you, the normal distribution and t distribution can be used for the confidence interval estimation. So based on that, we have third method, which is t method. T method is t is the t distribution. So this method is based on the t distribution, and we try to, and this is based essentially on the studentized form of the bootstrap statistics. And then the fourth one is basic confidence interval, and this is essentially based on the differences between each bootstrap replication. And finally, we will consider the bias corrected accelerated confidence interval, and we say indicate them by here PCA, and it is based on using the specific percentile of a bootstrap realization, which is a different way to compute the percentile. So first, let me try to explain you the basic behind the percentile method of confidence interval. So we know that we have a parameter of interest theta, and we want to estimate it by estimator theta hat, but it is difficult to obtain the finite sample properties of the sampling distribution of theta hat. So we try to use the bootstrap methodology, and we try to draw capital B number of bootstrap samples, and in each samples we try to compute theta hat, and this is denoted by here theta hat x b star. Means if you remember that x star b was the say bth bootstrap sample. So in every sample you have to compute the statistics, and which is denoted by theta hat x b star b. So since b usually we try to take a large number so that we can have a good histogram. Means if the b is very small, then the histogram will not actually look nice, right? And if b is large, then the histogram which is constructed using the bootstrap values, and that is called as bootstrap histogram, is a good approximation, is a close approximation to the true distribution of theta hat x. Right. So for example, just to illustrate you and just to convey my idea what I am trying to say, I have just taken here a possible histogram. So the values of theta hat have been computed for say b bootstrap samples, and they have been and based on that this histogram has been computed. So you can see here on the y axis we have the frequency, right. So yeah, this can be anything actually. This is only a representation of the histogram that we can obtain. So what we can obtain now here, that we have obtained here all the values of the theta hat xb, and we can just arrange them in increasing or decreasing order, and then we have to obtain basically the ordered value. So suppose if I say, suppose I have obtained 1000 bootstrap sample. So b is here 1000, and I try to rearrange them in the increasing order. So whatever is the maximum value, which is denoted by here theta hat star 1000, and I am writing this 1000 inside the parenthesis. So that is indicating the ordered value, which is the standard notation in say statistics. For example, if I say here I have three values here, x1 equal to say 5, and x2 is equal to say here 3, and x3 is equal to suppose here 8. So out of this I try to find out the maximum value, and the maximum value of among x1, x2 and x3, it is here, this is denoted by here x order 3, which is equal to here say here 8, and this is same as here x3. Then now x3 is out, so now I try to find out the maximum value between x1 and x2, and this comes out to be here, see here 5, and this is actually the first value x1, but as an ordered value this is the second largest value, and obviously then the minimum value x1 is denoted is the same as here x2, and which is here 3. So this is the meaning of this notation. So I try to arrange the values in the increasing order for theta hat star b, and then suppose I want to construct the 90% bootstrap confidence interval. So what I try to do here, I simply have to obtain the 50th quantile and 950th quantile. Why? Because we are taking here 1000 value. So I want here 90%. So what I want here, the area in the mid, this is 90%, and the area on the two sides is 5% each. So if I try to construct here the histogram, then this is going to be the, say, the 5th percentile, and this is going to be the 95th percentile. So essentially, if I try to consider this curve as a sampling distribution of theta hat, then essentially we are interested in finding out the 5th and 95th percentile, which are in this ordered value, they are the 50th and 950th value of theta hat star. Right. So at alpha is equal to 10%, alpha by 2 will become 0.05, and then I try to find out the value here, and these are your confidence interval. So that's what I'm trying to give you an idea that how the things are calculated. So now if I try to do it on the on a histogram, so I assume that we have obtained here, suppose large number of values of theta hat star b, say b goes from 1 to here b, and these values have been plotted here in this histogram, and this is the histogram that we have obtained. So we try to find out here in on the x axis, I try to find out the value such that the area on the left hand side is alpha by 2, and the area on the right hand side of this point is alpha by 2, and whatever are the values that we have obtained, these are the percentiles which are trying to indicate the, say, lower value of the confidence interval and upper value of the confidence interval. This is what I mean when I say that I want to construct the histogram of the bootstrapped value. So this area in between is 1 is alpha. So if I take alpha is equal to 10%, so this area is going to be 90%, and this area on the left hand side and right hand side will be 5%. Right. For example, so I try to show you here the same thing, that if I try to take here, for example, alpha is equal to 95%, which is the one of the popular values for the construction of confidence interval, then in this case, yeah, you have to take this area to be 95%, and this area will be 2.5% each. Right. So now if I try to formalize this procedure, what I am trying to do, I am trying to create the histogram, and then I am trying to use the 97.5th percentile and 2.5th percentile, and the area between these two percentile will be 95%. Right. So in order to achieve it, what I can do, all the sample statistics which are denoted here by theta hat x star b are ordered from low to high, and then we try to chop off the lowest 2.5% and highest 2.5% of this distribution. Right. And whatever is the middle 95% values, that will be the 95% of the total area, and the 2.5th percentile and 97.5th percentile will give us the lower and upper limit of the bootstrap percentile confidence interval. For example, if you try to see here, I try to make one more this type of plot. So, all the values of say this theta hat b star, they have been plotted here, and then I try to choose here a point where I can chop off the 2.5% on the left hand side and 2.5% on the right hand side. So, this area has been denoted in color red, and that area which is between the two limits, which is 95%, it is indicated by blue color, right. So, this theta hat alpha by 2 lower is the lower limit of the confidence interval, and theta hat alpha by 2 u is the upper limit of the confidence interval, and this by this approach you will get the confidence interval through percentile method. This is one of the most simple method to obtain. Okay, so now I come to the next approach, which is based on the use of standard normal distribution, normal 0 1. So, in this approach we simply try to use the basic concept that was used in the classical statistical inference for the construction of confidence interval, right. So, if you remember, if I try to take any value here theta hat, and if I try to find here find the difference with the theta, which is actually unknown, and if I try to divide it by his standard error of theta hat, usually it will follow a normal 0 1, particularly when your number of observations are large. So, that is why we try to take here capital B to be large enough so that this result hold true. So, now this theta is means given to us, but theta hat we do not know how to estimate what is the form of theta hat, exact form, and so finding out the exact sampling distribution of this quantity will be difficult. So, what I try to do here, instead of this theta hat, we try to take here the bootstrap estimator, and I try to consider here a statistics of this form, where theta hat is replaced by the bootstrap value of the statistics minus theta, and the standard error of theta hat is difficult to find. So, we try to use the bootstrap estimate of the standard error of theta hat. So, that we have denoted by VB, if you remember. So, now this statistics can be used to construct the confidence interval. So, in case if I take the confidence coefficient to be 1 minus alpha, then using this result that this statistic lies between minus z alpha by 2 and z alpha by 2, where z alpha by 2 is the upper alpha by 2 percent points on the normal 0 1 distribution. Using this thing I can simply solve it, and you can simply see here that theta 0 hat minus theta is less than minus z alpha by 2 times square root of VB, and this is z alpha by 2 square root of VB. And if you try to take a theta, this will be here theta 0 hat minus z alpha by 2 square root of VB, and on the right hand side this will be theta 0 hat plus z alpha by 2 square root of VB. So, theta 0 hat is essentially your bootstrap statistics which you have obtained, the bootstrap estimator of the parameter theta. So, this is the confidence interval which you will obtain. So, you can see here in this method you are assuming that this distribution is normal, right. So, and that is why you are using here the cutoff values as here z alpha by 2, right. But now the second approach is, suppose I do not know, and I can use the concept of t distribution, and I would like to do the same thing with the concept of t distribution, right. So, in the case of bootstrap t method for the construction of confidence interval, what we try to do, instead of taking this type of statistics which we have used here, right, we try to take the statistics which is of the form of, which has got the form of a studentized t statistics, and we try to create a studentized form of the bootstrap statistics. And in this thing, the standard error of the statistics can be computed by the bootstrap methodology, Now, there can be two methodology that you try to compute the bootstrap that you try to use the bootstrap estimate of every replicate, or you try to use the bootstrap estimate of the variance. So, based on that we have got two different methodologies, but in this case we are simply trying to say use the t statistics which has been constructed on the basis of bootstrap distribution and try to compute the cutoff values which are denoted by in general here as a t cutoff, and then try to use the general structure of the confidence interval like as bootstrap statistics plus minus the critical value which is denoted as t cutoff, and then the bootstrap standard error, right, where this alpha is between 0 and 1. So, this will also give you another type of bootstrap confidence interval. So, in this slide I have given you the basic idea behind. Now, how to do it? Let me try to show you here. So, what we try to do here, in this approach we try to consider the form of student t statistics. So, this is the value of the bootstrap estimator which we try to obtain in every bootstrap sample, and then I try to construct here the statistics theta hat x b star which is from the bth sample minus theta hat x underscore and divided by the bootstrap standard error of the statistics, right. And then we try to take large number of bootstrap sample so that the approximation holds good, and since we have got the large number of observations, so we can construct the histogram of this value which are obtained here, which are denoted here as a t star b. So, t star b is the value of the studentized t statistics which is based on the bootstrap sample number b, small b, right. And in case if you try to construct this type of histogram of this of the values of t star b, this will be a close approximation to the t distribution of theta hat x minus theta divided by the standard error of theta hat x, where the standard error of theta x is closely and well approximated by the quantity t Vb. So, that is the basic idea. So, if you try to see, we have used the classical concept of construction of the t statistics, and then we have used it in the construction of a similar statistics based on the bootstrap samples, right. So, now the final form of the t star b that will emerge is that for every bootstrap sample try to create this tb star where the value of the parameter will be obtained for each and every bootstrap sample minus theta hat x, and try to use the bootstrap sample and compute its standard error. So, you have you try to suppose I try to take here the sample number 1, I try to obtain here theta hat say based on the bootstrap, and then based on this sample S1 itself I try to find out the standard error, because you will have a sample of size small n. So, from that you can compute simply the variance and then take its standard take its say positive square root. So, that will give you the value of the estimator as well as the value of the standard error for each and every bootstrap sample, right. So, now you try to repeat this for a large number of bootstrap sample, and since the b is large, so we can construct here a histogram based on this tb star values. Okay. Now, once you create this type of histogram, then again you have to define the critical values. So, as we have discussed, these critical values are essentially the percentiles. So, we try to compute these percentiles like this, means we have here all sorts of values of TB star, something like this, which are scattered all over this distribution, and we try to find out the proportion of the TB star value which are smaller than say here T alpha, right. And what is your here T alpha? T alpha is the alphath quantile. So, I am simply trying to say that how, so first you try to find out the alphath quantile, say 5th quantile, 95th quantile, etc., and then try to see that how many values of the TB star which you have estimated on the basis of bootstrap sample are smaller than T alpha. So, you can see here all these values. I will try to now mark them in red color, right. Suppose these are the values which are say smaller than say here T alpha, right. So, I try to compute the number and I try to divide it by the total number of values. So, this will give me the proportion. So, from there I can compute this alpha, where alpha will be between 0 and 1. So, now for example, if I say suppose I choose b is equal to 1000, then I need suppose 5% and 95% quantiles on the left hand side. Suppose this is 5% and this is here 5%. So, this value will be 5th quantile and this value on the right hand side will be 95th quantile. Suppose I want to have this thing. So, what I can do, that I have got here the value of TB star, I try to order them as I shown you earlier, and then I just try to choose the largest value among this the values of TB star and the 9/50th largest value of the values of TB star, and then these are going to give us the critical values. Then what will happen? Then now in case if I try to recreate this thing in the form of some histogram like over here, then what will happen if I have partitioned this into two parts such that this part is alpha by 2% and this part is alpha by 2%, then whatever are the values on the x axis, they are going to give us an estimate of the T value, I mean the critical value, which looks like as if this is based on the T distribution, and then I can use the classical approach of the confidence interval estimation, something like theta hat plus minus standard error of theta hat into the critical value, which I have explained you here. You can see here this approach. So, now I have estimated this T cutoff using this histogram, and then I can use here theta hat x and then the bootstrap standard error of theta hat, and then this critical value is obtained from this constructed histogram, right. So, T alpha by 2L is going to denote the say the value on the x axis corresponding to which say alpha by 2% points are less than T alpha, and similarly I can compute here the upper limit like as here, right. यहाँ पर जो भी इसको एडिटिंग कर रहे होंगे उनसे एक रिक्वेस्ट है कि इस स्लाइड में एक गलती है, ये जो मैं इसको लाल कलर में दिखा रहा हूँ, ये जो वैल्यू है माइनस, ये इसको प्लस होना है, तो आप इसको प्लीज़ प्लस कर दीजिएगा। ये है स्लाइड नंबर 16 में, राइट। और मैं इसके आगे से अपना काम कंटिन्यू कर रहा हूँ। So, this is how we can obtain the confidence limit using the T method, and in brief, if I try to comprehend all the results whatever I have used here, in general I can say the 101 minus alpha % confidence interval based on the bootstrap T methodology for the parameter theta for alpha between 0 and 1 will look like theta 0 hat. If you remember, you had defined it to be the bootstrap estimator of theta, and VB here is defined as the bootstrap variance, right. And here I have used here 1 minus alpha by 2 and alpha by 2 just to make it here more general, that if the distribution is not exactly symmetric, then if you want to use the bootstrap T method over here, then at least you should be able to use it. Okay, now I give you a very quick review of the bootstrap basic confidence interval. Means this is another type of approach to construct the confidence interval using the bootstrap methodology. Right, it is difficult for me to give you the complete details, as we have not covered the entire statistics and you need something more, but I will just try to give you an idea. This confidence interval is also called as NPTEL or empirical confidence interval, and in this case suppose T0 be the value of the statistics in the original sample. Right, if you remember in the example of correlation coefficient, I had computed the correlation coefficient of hours. So this is the value of T0 statistics or statistics in the original sample, and let tau alpha be the percentile of the distribution of bootstrap realization. So you try to estimate your parameter theta by theta hat using the bootstrap estimators, and you have large number of values of these estimators, and then you try to construct the bootstrap histogram, and from there you try to compute the percentile. So this basic confidence interval is actually based on the computation of differences between each bootstrap replication and T0, and after this it tries to find out the distribution and compute the percentile of this distribution. Details we are not giving here. So we use this approach to construct to find out the percentile, and then we try to construct the 101 minus alpha % confidence interval using this expression. So after doing algebra, you will obtain this expression twice of T0 minus tau 1 minus alpha by 2 twice of T0 minus tau alpha by 2. Right. So similarly, I will try to give you a quick review of another approach to construct the bootstrap confidence interval. This is bootstrap bias corrected accelerated confidence interval, which is shortly called as BCA. A is in the subscript, and BCA stand for bias corrected. This BC stands for bias corrected, and this here A, this stands for accelerated. So actually this BCA intervals use percentile of the bootstrap distribution, but they do not necessarily use the 100th alpha or 101 minus alpha percentile. Actually they are computed in a different way, and it depends on the something called acceleration parameter and bias correction factor Z0 hat. जो भी यहाँ पे करेक्शन, जो भी इसको एडिटिंग करते समय एक यहाँ पे करेक्शन कर दीजिएगा, ये मैंने एक वैल्यू यहाँ पे लिखी है A, इसको हटाना है, राइट। तो ये वाली वैल्यू मैं आपको फिर से लाल में करके दिखा रहा हूँ, ये जो A है इसको डिलीट कर दीजिएगा इस पूरी स्लाइड से, और मैं अपनी रिकॉर्डिंग को कंटिन्यू कर रहा हूँ. Okay, so once you try to do all the algebra and all the statistical tool, then the final expression of 101 minus alpha % confidence interval comes out to be here like this, which the lower limit is connoted by theta hat star alpha 1 inside the parenthesis, and upper limit is denoted by theta hat star alpha 2 inside the parenthesis, and they are in briefly I am trying to denote the confidence limit which we are going to obtain on the basis of data as theta hat L and theta hat U. Right, where this this alpha 1 is actually the value from the CDF of normal 0 1, and this alpha 1 is the value of the CDF at this point. Right, and similarly this alpha 2 is the value of the CDF of normal 0 1 at this point. And you can see here that these two values which I have marked here, they depend on say factor like Z0 hat A hat.
Now, how to compute these two values? So, this bias correction factor in this case is estimated by Z0 hat, and if you try to see, it is based on the inverse of the CDF of normal 0 1. So, phi inverse is indicating the inverse CDF of inverse cumulative distribution function of normal 0 1, and this is based on the value of the proportion of the values of bootstrap statistics which are smaller than theta hat, right. And this actually bias correction factor essentially measures the median bias of theta hat star. That means, the median value of theta hat star b minus theta hat, right. And the second factor, which is the acceleration factor, actually this is calculated using the jackknife approach, which we are not using here. So, I am not giving you here the details, right. Now, just to give you an idea that between these two types of methods, which are based on percentile and on the concept of using the sampling distribution, how one can choose. Well, these are only the guidelines, but they have to be followed in a proper way. So, what I can say in a very simple language, that when the bootstrap distribution is symmetric and bell shaped, then any of the percentile method or the T method can be used. And when the bootstrap distribution is not symmetric or not bell shaped, then the percentile method is better to use, right. And similarly, there are other type of constraints for other types of situation where these different types of confidence intervals can be used. Now, before I conclude the lecture, let me try to give you some cautions which are to be kept in mind when we are trying to use the bootstrap confidence interval. Definitely, you know that bootstrap confidence interval are really trying to approximate the true confidence interval. So, definitely when you are trying to approximate, you have to be careful, and the approximation has to be used at a right place and in the correct situation. So, first caution is that the bootstrap sample usually does not give reliable estimate when the sample size is small, say very small. Say, as a rule of thumb, I can say if the sample size is smaller than 2, then it is difficult to believe on the accuracy of the this bootstrap confidence intervals. And the bootstrap method does not give reliable results in those distributions that have infinite second moments. There are some situation where the second moment does not exist. So, when the moment does not exist, you cannot estimate the variability using the bootstrap variance, and so in that case it is not advisable to use the bootstrap confidence interval. And when you see that the values are in such a way such that the sample values have got some extreme values, means you try to estimate theta hat square b, and if you try to see from the histogram that some of the values are extreme, they are quite away from the usual values. For example, all the values are between say 1 to say here 20, and suddenly there is some value which is 200 or 2000 or something like this. Then in those situations, when we have extreme values in the data, in the bootstrap values, then this bootstrap confidence interval are not reliable. Actually, in this case, even the classical statistics has different types of tools to handle the situation. So, the same story continues in the case of bootstrap samples also. And whatever the explained methods we have considered here for the construction of confidence interval, they work quite satisfactorily if the bootstrap distribution of the statistics is smooth and symmetric. This idea you can get from by plotting the bootstrapped values using histogram or plot density, and there are several types of option in R to plot such values, and from there you can have a fair idea whether you have to use the bootstrap confidence interval or not. So, what is the rule? That first we try to look at a plot of the bootstrap distribution, and many times the statistical tools are based on the normal distribution. So, in that case we would also like to compare whether the bootstrap distribution is close enough to the normal distribution or not. So, this can be achieved by normal probability plot. In R, there is an option what is called as Q-key plots. They can help you in plotting the normal probability plot, and I will show you in the R that it is automatically obtained when you are trying to do the Bootstrap confidence interval. And if the Bootstrap distribution is highly skewed, or there are too many spikes and gaps which are clearly appearing in the histogram or the density curve, then in those situations it is not advisable to use the Bootstrap confidence interval, but that is also true for the usual tools of statistical inference. Okay, so after giving you this limitation, now just to make you convinced, I try to give you an example that how this Bootstrap methodology is being used in data sciences. So, machine learning is a part of the data sciences, which we all know. So, this Bootstrap methodology is used in machine learning with a different name, and this is actually this procedure is actually used to estimate the skill of a machine learning model. But before I start, let me make it very clear that I am not really an expert in machine learning. I know little bit to survive, right? So, don't expect too much and don't ask many questions, right? So, okay, the approach here is very simple, that first we try to train the model on the sample and evaluate the skills of the model on those samples not included in the sample. And these samples not included in the given sample are called as out of bag sample, and they are briefly denoted by OOB sample. That is the popular terminology which is used in machine learning, right? And how do we estimate the skill of the model using the Bootstrap method? So, this is here the procedure. The first step is this: try to choose B, which is your number of Bootstrap samples, and usually it is taken to be a large number, and then you try to draw a sample of size n, and then from there you try to draw B number of Bootstrap sample, and for each of the Bootstrap sample draw a sample of size n by SRSWR, usual approach. Then you try to fit a model on the data sample, estimate the skill of the model on the out of bag sample, and after that, once you obtain this thing, calculate the mean of the sample of model skill estimates. So, you can see here, if you try to translate this terminology, or if you ask me to translate this terminology in the classical statistics, this is nothing but what we have done in the Bootstrap methodology, right. So, now this is the time to stop after having a long lecture. Well, that was important. But before I go further, let me assure you, whatever I have taught you in this long lecture, in R they can be done in a fraction of a second. You simply have to use one command and it will give you all sorts of confidence interval. But as I said, my objective is not to produce compounders. I want to produce good qualified data scientist. So, that is why I have taken this topic over here. Now, once I try to use the R software, you will see it will give you all the 4 or 5 outcomes based on this confidence interval. But your trouble is this: which one to choose and what these things are giving you. All the confidence limits you will see, they are going to be quite different from each other. So, this type of knowledge, this type of basic fundamental will help you in choosing the correct confidence interval. And when you are using this Bootstrap methodology in a bigger data set having millions and billions of observation, you will not have any opportunity to look into the data. You will simply be doing first the data cleaning,
And during data cleaning, you have to take care whether your observations have spikes or say gaps or extreme values. And then based on that, you have to choose the correct confidence interval. So that was my objective, to choose these topics over here before I go to R software. So you try to please revise this thing, try to settle down these things, and try to read from the book also. Means I have followed these lectures from the book of Bradley Efron, which I told you earlier. So you can have a look in that book, you will get more knowledge, more clarity, and I will see you in the next lecture. Till then, goodbye.